Hello everyone, my name is Yuwen. In this paper, I emerged encryption algorithm based on 3D chaotic map and DNA operations. Contents: Introduction 1, 2. The model of system. 3. Encryption scheme. 4. Simulation. 5. Security analysis. Introduction. With the advent of the electronic information age, the ways of information exchange have been constantly enriched. In process of communication, a large amount of information comes along, and the security of transmission and storage of information on the internet is threatened. Therefore, how to ensure that this private information images are not retracted and stored in the transmission process has been a rich hospital. The model of system. In this paper, the three-dimensional discrete chaotic map is obtained in Ref 31. The chaotic map can be described by the following equation, where A, B, C are parameters of 3D discrete map. When parameters A, B, C are 4, 4, 2, and the initial value x0, y0, and z0 are these. The phase diagram is shown in Figure 1a. Phase the system parameter B is this. The Lyapunov independent spectrum is shown in Figure 1b. The bifurcation diagram of the chaotic map is plotted in Figure 1c. It's shown that this condition of system has good chaotic dynamic behavior, and it can be applied in image encryption field. Figure 1. Phase diagram, LES and DBS of 3D discrete chaotic map. Encryption scheme. The secret sequence generator. The plain image is introduced as a parameter to SHA function. The KK with 256 bits is generated, and the K is divided into 32 groups. L consists of 8 bits numbers. K can be divided as follows: K, Ki. The new stream K can be obtained. The new initial values for chaotic system can be divided as Ka, Kb, Kc. Permutation operation. Input gray plane image P. Step 2. Use the initial value S1, Y1, Z1, and U1. Then iterate the chaotic map for this time. In the end, K sequence SYZ can be generated. The four integrate sequences S1, Y1, Z1 are obtained from following formulas. Step 2. Divide the K sequence S1, Y1, Z1 into three groups that can be expressed as J1, J2, J3. According to the first procedures, value P1 of grey emerge P set index this. When index is 1, we get K sequence J1 that is used to permutate gray image. Step 4. In this step, permutation method uses another assume J1 is chosen according to step 3, with index is 1. Diffusion operation. Step 1. Transform permuted image into a barometric D. Then, according to DNA encoding L1 ruler, DNA metric W can be obtained. Step 2. The state variables S, Y, Z can be obtained by the equation 7. S1, Y1, and Z1 can be calculated in following S1, Y1, Z1. Step 4. Convert key 2 to a DNA metric key 3 with the encoding L1 ruler. The encrypted S metric is calculated as follows. Step 4. Decoding the DNA metric S by decoding ruler L2. Finally, the cipher image this is obtained. The encryption flowchart is shown in Figure 2. Plan image SAHA function. Security key. DNA encoding, DNA metric permutation, diffusion operation, DNA decoding. Finally, cipher image S obtained. Simulation. Firstly, the initial values and parameters of 3D discrete chaotic system are set as S0, Y0, and Z0 are this, A, B, C are this. Secondly, DNA encoding rulers L1 is E, and decoding L2 is 3, and iteration numbers L is 500. Lina as a grace image to be encrypted. Lastly, the encrypted and decrypted images are shown in Figure 3A to F. Figure 3. Simulation test the results. A. Plain image of Lina. B. Encrypted cipher image. C. Decrypted image of Lina. Security analysis. If the computing precision of the computer is this, only the key of 3D discrete chaotic system S0Y000ABC and the external key generated by SHA hash function space will be this. It means that our algorithm has a huge key space to resist all kinds of brute force attacks. Key sensitivity. In experiments, the key of key sensitivity scheme used S010Z0ABC, which belongs 3D discrete chaotic map as secret key. Figure 4 shows the decrypted image of the encrypted image of slightly changing the value of parameter and keeping remain parameters same. The experimental results shown in Figure 4. Key sensitivity testers. Histogram analysis. The histogram counters its distribution of image pixels and the cipher image histogram obtained after encryption should be as evenly distributed as possible. Here is the distribution state that Lina image and encrypted cipher should show as shown in the figure below. The gray histograms of Lina and its cipher image is shown in Figure 4. Lina. A. Lina histogram. B. Histogram of cipher image of Lina. Correlation analysis. In order to visually observe the correlation changes of images before and after encryption, Figure 6 shows the correlation of the horizontal organization in the plane image Lina and its cipher image. Figure 6. Correlation of two organization purpose of the plane image Lina and its cipher image. It can be seen from the table 3 that the correlation and correlation coefficients of plane image are all above 19%, but the correlation coefficients of the adjacent elements of cipher text are all approximately 0. The correlation index of this algorithm is better than that of our other algorithm. Table 4. Comparison of image correlation coefficients in plain text and ciphertext. Information entropy. It can be seen from Table 5 that information entropy of our algorithm is very close to the ideal value, indicating that the information leakage of ciphertext is very small and the algorithm is safe. Table 5. Information entropy of ciphertext image with different algorithm. Last, reference. Thanks.